Hi, everyone. This is sample test 1 for Math 1342, Calculus 2. This was an old first test of mine in a previous semester, and so we will go over this in preparation for our exam. Sort of understand my caution, right? Our test will have different problems, of course, and it might be slightly longer or slightly shorter. I haven't written it yet. It just depends on how I write the test. But the sort of general difficulty and general types of questions are the same. And so this sample test is a very nice practice for us. Okay, first one, partial fractions. Well, we want to write down the general form. When we look at the integrand, we see distinct linear, we see irreducible quadratic. And so the general form will be a over x plus bx plus c over this irreducible quadratic. Now, next step, we get a common denominator, which is just the product of the two, x times x squared plus 4. We multiply a by x squared plus 4, and we multiply bx plus c times x. I sometimes will multiply everything out, but I think I can see the terms that I have here. So I will go ahead and equate my numerators because, right, we want this to equal this integrand, and they have the same denominator. And so I can equate numerators. In my integral, I see 1 times x squared plus, I have 5 times x, and then plus, the constant is 8, and this will equal, well, something times x squared plus something times x, and then plus some constant. And the x squared, you see, we have an ax squared. We also here have bx squared. So here we put a plus b. Then in front of the x, well, it's just here, c times x. So we just have c here. And then my constant is 4 times a, 4a. This leads to 3 equations and 3 unknowns. Here, this coefficient equals the coefficient in front of x squared on the other side, and this coefficient equals the coefficient in front of the x on the other side. Similarly here, this coefficient and this coefficient, the constant parts will be equal. So my equations are a plus b equals 1. We have c equals 5. We have 4a equals 8. Well, this system is very straightforward to solve. Sometimes they're more involved, but this one is not too bad. We have a as 2. We've already solved c as 5. And so now I can just solve for b. b would be 1 minus a, which is -1. b is -1. Now I am ready to write down my integral. This is a is 2. And then I have b x plus c over this part, x squared plus 4. Now I remember when I gave this test, okay, this is where a lot of, not a lot, but some of my students got stuck because they weren't sure how to integrate this term. But the whole thing that is boxed is not substitution. What we need to do is break this into a sum of 2 terms. Maybe I'll do that in my next step. First of all, you notice I can already integrate this, right? This part. This is just 2 ln absolute value of x. And then I will have, say, minus the integral of x over x squared plus 4. And then I will have a plus the integral of 5 over x squared plus 4 dx. Okay. Now, this second term is the substitution one. Let me scroll up slightly. It's this one. U is x squared plus 4, and du is 2x dx. Now, we have x dx handed to us in our integral. This is 1/2 du. This is what I need for substitution, but it's only on this term because you see this part, this is a tan inverse. We have maybe I will write as part of my work over here. Recall, if we integrate 1 over x squared plus a squared dx, we get 1 over a, tan inverse of x over a, tan inverse x over a, and then plus c. I don't have room for my plus c. I can move this back. But this was something that we did in class. And it's something that we need to remember because it comes up, for instance, right here, partial fractions. And so I'm going to come down here. We have 2 ln absolute value of x. This one, we have an integral is 1 over u times 1/2 du. And then I can go ahead and just integrate this last term. It would be 5 over 2 tan inverse of x over 2. Okay. Now I just have a few more things to do. 2 ln absolute value of x. Then I integrate with respect to u. And these parts I am still copying. 5 over 2 tan inverse of x over 2. Now let me move some things and I can put my final answer. Now my space is better. There is a plus c here, but my final step is I just go back to x. So this is 2 ln absolute value of x minus, we have 1/2 ln. I could leave the absolute values, but I don't have to because inside here is always non-negative. And then I have 5 over 2 tan inverse of x over 2 plus c. This is my answer to number 1. 2a, well, we see a product and it is not an obvious substitution. This suggests by parts. And if we follow our acronym, LIATE, I do not have a log, I do not have inverse trig, but I do have this. I have the algebraic. U is 5t, and dv is cosine 2t times dt. And you should check if you take and multiply u dv, you should get everything except the integral sign, as we see here. Now, differentiate. This is du. We have 5 dt, and integrate. When we integrate the cosine, we get positive sign, but here we have this 2t on the inside, so we will have a 1 over 2 coming out. Integration by parts goes uv minus the integral of v du. And let me put a box around this part. So we have uv, which is 5t over 2 sine of 2t, and then minus the integral of 5 over 2 sine of 2t dt. This was integration by parts, uv minus the integral of v du. Well, the only thing left to do here is to integrate this term. And when we integrate sine, we get negative cosine. But you see, I have this negative here. So everything this will be a plus once I integrate, right? I have 5t over 2 sine of 2t. And then I integrate. Integral of sine, like I said, negative cosine, but with a minus in front, this is positive. And I will have 5 over 4 cosine of 2t, because I get another 1 over 2 coming out when I integrate. This is my final answer. And don't forget your plus c, right? This is 2a. Now, 2b. You notice I see another product, but the difference here is I see an inside function and a multiple of its derivative. So this is not by parts. This is substitution, where u is up inside the exponent of e, du is minus 10t dt. And we have just t dt. This will be negative 1 over 10 du. So this is all my substitution box. So I have an integral. This is where I convert to an integral of u. It goes e to the u. And then t dt is minus 1 over 10 du. Now we integrate. This is the fun part because when we integrate e to the u, we get e to the u, and the minus 1 over 10 just comes along. Finally go back to t, and I'll just put my answer here. Minus 1 over 10 e to the 4 minus 5t squared plus c. This is my final answer. It was substitution in this problem. Number 3, we have an improper integral. And you notice this is type 2 because here, my limits of integration are finite numbers. And if you're not careful, it looks like a definite integral, but it is not, because this integrand, you see, is undefined here. Well, the denominator is 0, so the whole integrand, that's right, undefined at -3. We have an infinite discontinuity at x equals -3. So we start with the definition. This part is important. We want a limit. Let's say as b goes to -3, technically it's a one-sided limit. Like I have said, we're coming from bigger numbers. And then we have an integral from b to 1. And I can go ahead and write this as a power. It's a -3/2 power. I have a limit as b goes to -3. Now we integrate. Remember, every improper integral is first a definite integral. That's this part, and then a limit. And both of these should be part of your work. So we integrate. We add a power, which is x plus 3 to the -1/2, and divide by the higher power. And then we will evaluate this between b and 1. We have a limit as b goes to -3 from the right. And now this part is evaluating. My antiderivative, well, I have a -2 in the numerator. And then in the denominator, you notice I have a square root. So I'll go ahead and do it like this. I evaluate at the upper limit of integration, and I get 3 plus 1 under here, which is 4, and then subtract off, but it's negative. I could have just called it plus, but I am doing minus just to show the fundamental theorem of calculus here. And then evaluate the lower limit, b plus 3. Okay, that was my definite integral, right? First we do this, that is here, and that is here. The last step of an improper integral is to take a limit. b is approaching -3 from values bigger than -3. Very nice. Under here is going to 0. Underneath the radical and square root of 0 is 0. So my denominator is going to 0. That means the fraction, well, it's positive. So this is going to infinity. And the answer here is diverges. The limit does not exist as a finite number. The improper integral diverges. Now we have Simpsons Rule. We want to estimate a definite integral using Simpsons Rule. Well, the first step, whether you have Simpsons Rule or trapezoid rule, the first step is always calculate delta x. This is b minus a over n. Here we are told n equals 4. So this is 8 over 4. Delta x is 2. Next step, write down your partition. You start with the lower limit of integration, march forward by delta x, which is 2, until you hit the upper limit of integration. This is my partition. And you see I have 1, 2, 3, 4 subintervals. Wonderful. Now, here comes Simpsons Rule. The formula is a delta x over 3. We have f of -1, and then the coefficients will go 4, and then 2, and then 4, and then the very last comes with coefficient 1. Okay, so this is it. I'm going to write it with the actual function. So here, this f is the integrand, right? Let's go one more step. Delta x is 2, so we have 2 over 3, and then this is just ln 2. plus we have 4, evaluate at 1. We have another ln 2. And then we have 2, evaluate at 3. We have 9 plus 1, so ln of 10. We have 4. Let's see. At 5, we'll have ln of 26. And finally, we have ln of 49 plus 1, 50. Then, okay, I don't have anything yet, right? We enter this as one expression in our calculator and then round. So when I do, I get this is approximately 16 point, and then it has 676, but then it goes 87, 87. So to round, this would be 9. Okay, 4 decimal places. This would be my final answer for number 4. Number 5, you see, we have a third order Maclaurin polynomial. Then we use it to approximate something, and we see we have reasonable upper bound on error coming. Okay, so when I go to make this chart, right, what I always do, this is center at 0. So I'll have k, the kth derivative as a function of x, the kth derivative evaluated at my center, which is 0. And finally, the kth derivative evaluated at my center divided by k factorial. Kth derivative evaluated at my center divided by k factorial. Now, because I know error is coming up, I will go ahead and take one more derivative. So this needs third order. And the fourth one, I'll just use in my error estimate. I will not evaluate at the center or divide by k factorial, for example. The function is e to the minus x over 2. Now we just start differentiating. We have minus 1/2 e to the minus x over 2. We have positive 1 over 4 e to the minus x over 2. We have negative 1 over 8 e to the minus x over 2. And finally, we will have a positive 1 over 16 e to the minus x over 2. That's just being used in part C. Now, evaluate at the center. The nice thing is, this part, all evaluated at 0, is just 1. E to the 0 is 1. And so my coefficients, well, evaluating at the center at least, we have 1, we have minus 1/2, 1/4, and negative 1 over 8. Now, this part is my coefficients of my polynomial, right? And I need to divide by k factorial. 0 factorial is 1, 1 factorial is 1, 2 factorial is 2, and 3 factorial is 6. So this is minus 1 over 48. Now we can just write down the polynomial. This column gives us the coefficients. So I have 1 minus 1/2 x. I have plus 1 over 8 x squared and minus 1 over 48 x cubed. This is my third order Maclaurin polynomial for this function. Now we have to use it though. Let me move this up so we can read the directions. We want to estimate e to the minus 0.1. So you know how I do this. This is what I want to estimate. And my function is here. And so I just line it up and compare. We would have minus x over 2 equals negative 0.1, and we solve for x. So let's use x equals positive 0.2. So that means what we want is, maybe I'll do it in this color, 1 minus 0.2 over 2 plus 0.2 squared over 8, and then minus 0.2 cubed over 48. Okay, that is this polynomial estimation. So then it says round to 4 decimal places. Let me see what I get. I have, this is 0.9048. Okay, this is our polynomial. The thing is, even though you use your calculator for this, it is polynomial evaluation, which is a fantastic thing. Now, part C. reasonable upper bound on error. Okay, the first step in this is we write out the general form. So this is third order. We have centered at 0, and it looks like this. Don't forget the absolute values, but it looks like the very next term, which was the fourth derivative at some c over 4 factorial. And then we have x to the fourth, okay, because my center is 0. Now we already calculated the fourth derivative, so I could just write that. Well, you see in this example, and this doesn't always happen, but in this example, my fourth derivative is positive, and x to the fourth is always non-negative. So I don't need to write my absolute values in the next step. But I have, in the numerator, I have e to the minus c over 2, and there's a 16 in the denominator, and then down here is a 4 factorial, and in the numerator I have an x to the fourth. And this is for some c, and also x for that matter, in, while we write down the interval. You notice it's given to us, it's right here. We want to be within 0.2 of the center. So if you start at 0 and you move 0.2 in each direction, we get minus 0.2 to 0.2. So for some c in this interval, from minus 0.2 to 0.2. Great. Well, here comes our two-step process. We want to make this part as big as possible on our interval, and independently, we want to make this part as big as possible on our interval. So let's do this now. First of all, let's do the pink. The pink, well, this is exponential decay because of the minus sign, so this is definitely decreasing. And so we will use, well, you have a decreasing function on a closed interval. The largest it can be is the left endpoint. We use c equals minus 0.2. That's our first less than or equal to. When we do this, evaluate at c as minus 0.2, we get e to the 0.1 over 16. And then we still have this. Now for the second part, you can use either value of x. We could either use x is 0.2 or the other one, because what we want to do is just move as far away from the center as possible. Far away from the center as possible. And that occurs really at either 0.2 or minus 0.2. So we have this second less than or equal to in my two-step process will be e to the 0.1, and then we have 0.2 to the fourth power divided by 16 times 4 factorial. Now, what happens when you put this in your calculator? I'm going to tell you, and then I'll talk about why that is not the best upper bound to use. We have 5 zeros followed by 460. Now, I personally would accept this, but it's good to know it is not the best answer because it's circular, right? We are using polynomial here in part B. In fact, we use a polynomial to estimate e to something, e to the minus 0.1. And then I ask you, how close is that estimation? And you say, well, it's e to the 0.1 times something close. If you don't know how big this is, how are you going to know how close you are? And so that's kind of the issue here. So it's better to not, as we've discussed, not have e to the 0.1 in your error estimate. And how we would go about this, well, this is the e to the 1 over 10, and that's certainly less than or equal to 2. Well, it's strictly less than 2 because e, which is a number between 2 and 3, is less than 2 to the 10th. Definitely, that's a really big number. So I can just replace e to the 0.1 with 2 and put a symbol like this, and I will have a different upper bound. It's bigger, but it's better in the sense of it is not circular. Okay, so this other one here, rounded past the leading zeros, Well, we still have 5 zeros. 1, 2, 3, 4, 5, and then we have 8, 3, 3. Just like I said, it's a larger number. The nice thing about this one is it's no longer circular. This one is better because it's not circular. Okay, so this is the end of our reasonable upper bound on error problem, which was 5C. Now we move into the very last problem on the test. This one is manipulating power series. We are given a Maclaurin series for the sine, and first part, we want to find a power series representation for an antiderivative for this function, but we have a few steps to do to get there. The first thing we need to do, you see this is composition followed by a multiply through by a power, and you definitely want to compose first. Okay, so the sine of x cubed. Well, I find it easier. Summation notation. We can also work writing out our terms. But if we look ahead, how do we have to use this? We are going to need the first two non-zero terms to do something. So you see, I'm going to need my terms anyways. So I think I'll just write out my terms for part A. But summation notation is perfectly fine. In fact, if we read the directions, we give the series in summation notation, or we list the first four non-zero terms. So let's write out our terms. This would be x cubed. So this is composition in this first step. We have x cubed over 3 factorial. We have plus, we have x cubed to the 5th over 5 factorial. And then we have a minus, we have x cubed to the 7th over 7 factorial. The next one will be plus. So there's 4 non-zero terms. Great. But I'm not finished because we want to write each one of these as x to a power before I divide by x squared, for example. So let me take one more step. This is x to the 9th over 3 factorial. This one is x to the 15th over 5 factorial. And then the final term, we have an x to the 21 over 7 factorial. And then it continues. So this is sine of x cubed. Next step, we divide by x squared. And all we need to do is just lower the power on each term by 2, right? I'm using, if you have, say, x to the a over x to the b is x to the a minus b, right? This property of exponents. And so if I divide every single term by x squared, I'm just lowering the exponent by 2. This will be x minus x to the 7th over 3 factorial plus x to the 13th over 5 factorial, and then minus x to the 19th over 7 factorial. This is power series representation for sine of x cubed divided by x squared. And now the final part, which is our answer, right? Part A, we have multiple steps to get there. We want to integrate this power series. So this is my final answer, the integral here. We have c plus, that's our constant, and then add a power, divide by the higher power, add a power, divide by the higher power, add a power, divide by the higher power. That's all we're doing. Each term is just polynomial. So we have x squared over 2. We have minus x to the 8 over, I'll just leave the factorials, 3 factorial times 8, and then plus x to the 14 over, we have 5 factorial times 14, this is the times, and then we have minus, we have x to the add a power 20 over, we have 7 factorial times 20. This is the first 4 non-zero terms. Now, maybe I'll go through before we move on, because some people like to write summation notation. Personally, me, I prefer it because you see every single operation we did, instead of having to work and do it 4 times, we can just do it 1 time. And so I will over here do the exact same thing in summation notation. Let's look at the summation notation here. This is -1 to the k. The first step is still composition. So we have x cubed to the 2k plus 1 over, we have 2k plus 1 factorial. But then you see we need to simplify it. And that is just like we did here. Power to a power, we multiply. So in summation notation, the nice thing is we just have to do this, like I said, 1 time. This is -1 to the k. This is x to the, we have 6k plus 3. I'm just multiplying 3 times 2k plus 1, and then divided by here, 2k plus 1 factorial. Next step, we divide by x squared. And like I said, which we did 4 times before, this just lowers the exponent by 2. So this, we have a sum, k equals 0 to infinity. We have -1 to the k. Subtract 2 from the exponent. This would be 6k plus 1. And then this still stays the same. 2k plus 1 factorial. Now we integrate our final step for part A. Okay, this is also summation notation, but I need c plus. We keep the -1 to the k, and then we just add a power. This would be 6k plus 2, and then divide by the higher power. So I'll keep the factorial. We have 2k plus 1 factorial, and then we multiply 6k plus 2. Okay, add a power, divide by the higher power. It's just polynomial integration, except we're doing it to infinitely many terms. I have in fact worked part A both ways. I hadn't intended to, but it's perfectly fine, part of our review. Now we move on to part B. We want the first 2 non-zero terms, and we want to use them to approximate a definite integral, round 2 4 places. Well, first 2 non-zero terms would be here. Of course, we don't count the plus c. First 2 non-zero terms of, say, 1 antiderivative. Or you could just let k equals 0 and let k equals 1 in this. So what we want, the thing is we have already integrated. So we want x squared over 2. This is part of my antiderivative. And this, let's see, 3 factorial is 6. So this is x to the 8 over 48. And then we evaluate between 0.2 and 1. This is just 1/2 minus 1 over 48. And then we will have minus 0.2 squared over 2. And then we have plus 0.2 to the 8 over 48. This is just evaluating my antiderivative at the upper and lower limits of integration, 0.2 and 1. And then we round to 4 decimal places, which becomes 0.4592. And this is the end of this sample test. Good luck on the actual test. Thank you very much.